Hey folks, got another work and power example, and this one involves a variable force. You might want to take a moment to copy this down. I'll kind of explain what it is you're copying down. Uh, you have a 10-kilogram book bag. You're pulling it across the floor, let's say, and you have this unusual force acting on it, and the force is equal to 6x squared minus 60 newtons. Okay, so it's not a linear force, and it's not a constant force. And we're going to pull the book bag from the 4-meter mark to the 8-meter mark. And the starting kinetic energy, K naught, is 60 joules. And we're going to determine what's the final velocity of the book bag and what power is that force delivering right at the end of the motion. So at the 8-meter mark, what power, at what rate is that force adding energy to the book bag? Okay. All right, so if you need to pause for a second and copy this down, now would be a good time. All righty. So how do you find final velocity? All right. Well, here's some things you should not do, right? I wouldn't try to do like F equals ma and try to find a, and then use constant velocity or acceleration equations like v final squared equals v naught squared plus 2a delta x, because your force is not constant. Therefore, your acceleration is not constant. Therefore, those constant acceleration kinematic equations are all null and void. Okay. So, in a problem like this, the first thing you should do, and in all these problems, is determine what strategy you're going to employ to get your answer. Okay. So, in a problem like this, and you might pause for a second and see if you can predict what I'm going to say next. Seriously, like pause the video and see if you can map out, not do the whole problem, but just map out what you would do. So, what would you do? Okay. Well, there's only one force acting on the book bag. So what I'm going to do is first I'm going to find the work done, all right, by that force, and then that's going to equal the change in kinetic energy. Okay. Then I'm going to find the final kinetic energy because if I know the starting kinetic energy is 60, I know the change in kinetic energy, I can figure out the final kinetic energy, and then I'm going to find the final velocity. And then to find the power, we'll talk about that in a sec. But so here's my strategy. I've got to find the work done, and then that's going to be the change in kinetic energy in this case, and then I can find K final and B D. Now, the force is not constant, so I cannot use work equals force dot delta X. Okay, I cannot use that because F ain't constant, all right? So you have to use the definition of work, most general definition, okay, which is the following. Work is equal to the integral of F. Now, in this case, force is a function of X, so we're going to times dx, okay? Um, for our example, the force is 6x squared minus 60, dot dx, okay? And we're evaluating that from the 4-meter mark to the 8-meter mark. Now, a few people might ask, well, Mashar, why don't you just go from 0 to 4? It's still 4 meters, right? Well, the force values are different at 0, 4, and 8 meters, so you have to be careful and put the correct limits in here, okay? Now we're going to use our power rule, okay? So 6x squared will becomes 6x, you add 1 to the exponent and divide by that new exponent. So there's that part of it. And then it's 60x to the 0. If I integrate that, that becomes 60x to the 1 over 1, okay? Now I'll rewrite this. The first term becomes a 2x cubed, and the second term becomes a 60x, and we are evaluating that from 4 to 8 meters, okay? So if I do this, I get the work done, 2 times 8 cubed, I get 1,024, minus 60 times 8 is 480, and then minus, and then I got to plug the 4 in. 4 cubed times 2, I get 128, and then minus, and then 60 times 4 is 240. And so this ends up being 544 minus negative 112, and I get a positive 656 joules. So that is the net work done on the book bag by that force. Okay, that's the only force acting on the book bag along the motion. Okay, so now we know net work. is change in kinetic energy, which is K final minus K naught. My change is positive 656. So by the way, the bag's speeding up because it's positive. K final, I don't know. K naught was 60. Okay, so now I know my K final is 716 joules. Okay, and now I know my velocity. My velocity final is root 2 K final over M. We derived that equation previous video. And if we use that, 2 times 716 all over 10, I get the square root of 143.2, and it's about 12.0 meters per second. Okay, so your book bag's cooking. It's moving about, it's about 27 miles per hour. It's pretty fast. You don't want to get in the way of that. All right, so we have solved for the final velocity of the book bag. Now, the second thing I asked you for was what's the power being delivered by that force at the end of the motion. Okay, so I'm asking for one specific spot in the motion. Therefore, we're looking for instantaneous power. So power instantaneous. Now, there's two versions of this. There's force dot velocity or dw dt. Well, I don't have work as a function of time, so I can't use this. Okay, so I have to use force times velocity. What's the force? So here I have to plug in. So force is 6x squared minus 60. And I'm looking at the end of the motion, so I'm looking at the 8-meter mark, so I have to plug in my 8 there. So if I plug in 8, I get 6 times 8 squared, I get, oops, sorry about that, 384. Okay, hold on one sec. All right, got that cleared up. Anyway, so we're plugging in 8 meters to figure out what's the force at that 8-meter mark. So I get 384 minus 60, okay, is 324. So that's my force in newtons. And the power instantaneous is that force, which is 324, times the velocity, which I just found. It's just about 12.0 meters per second. And I get, if I plug my numbers in correctly in the calculator, I get 3,888 watts, okay, which is a big number. We're adding energy to the book bag fairly quickly, and that's why it's speeding up so quickly and moving really fast, okay. All right, so I'm going to do one more example in the next video. Again, a key here. Last year, you all are using work equals force times x or force times delta x. We're beyond that now. Okay, for a lot of these problems, you're going to have to use the integral. Okay, and I know it's new for a lot of you, but you're just doing the polynomial rule here. You're integrating f dot dx, and you're just doing the inverse power rule, you know, for integral to figure out what the work is done by this weird non-constant force. I'll kind of show you an example. The next example I'm going to show you involves a spring, which is also a non-constant force, and we'll talk about using the integral again in that instance. See you in the next one.